Titan. A world shrouded in orange haze, where methane rains fall from alien skies and lakes of liquid hydrocarbons shimmer under the faint glow of distant Saturn. This isn't science fiction. This is the largest moon of Saturn, a place so eerily similar to early Earth yet so fundamentally different that it challenges everything we thought we knew about where life could exist in our solar system. When the Cassini spacecraft first pierced through Titan's thick atmosphere with its radar eyes, what it revealed was nothing short of extraordinary. Here was a moon, larger than the planet Mercury, with weather systems, seasonal cycles, and a hydrological system remarkably similar to Earth's, except instead of water, methane plays the starring role. Imagine standing on Titan's surface. The sky above you would be a perpetual twilight, a deep orange haze so thick that you wouldn't see Saturn hanging overhead, even though the giant planet would occupy a huge portion of the sky if the atmosphere were clear. The sun would be just a bright spot, its light filtered through hundreds of kilometers of nitrogen and methane, creating a dim illumination about 1,000 times darker than a clear day on Earth. The temperature around you would be a bone-chilling -179 degrees Celsius, cold enough that water ice becomes as hard as granite and methane exists as a liquid. The atmospheric pressure would be about 1.5 times that of Earth's at sea level, denser than our home planet, which means you could actually fly on Titan with wings attached to your arms, despite the moon's lower gravity. But what makes Titan truly fascinating isn't just its alien landscape. It's the fact that this frozen world might hold the keys to understanding the origins of life itself. The chemistry happening in Titan's atmosphere right now is thought to be similar to what occurred on Earth over 4 billion years ago, before life emerged and transformed our planet's atmosphere. Complex organic molecules are constantly being created in Titan's upper atmosphere, where ultraviolet light from the sun breaks apart methane and nitrogen molecules, allowing them to recombine into increasingly complex compounds. These organic molecules rain down onto the surface, accumulating over millions of years into layers that could be dozens of meters thick in some places. This organic material is everywhere on Titan, coating the surface in a reddish-brown layer that gives the moon its distinctive color. The story of how we came to understand Titan is itself a remarkable journey of human ingenuity and persistence. For centuries, Titan was just a point of light in telescopes, discovered by Christian Huygens in 1655, the first moon found orbiting Saturn and only the sixth moon discovered in the entire solar system. For over 300 years, Titan kept its secrets hidden behind that impenetrable atmosphere. Early astronomers could see that something was different about this moon. It appeared larger and more diffuse than other moons, a clue that it possessed a substantial atmosphere, but they had no idea just how substantial. It wasn't until 1944 that Gerard Kuiper spectroscopically detected methane in Titan's atmosphere, the first time a moon in our solar system was confirmed to have an atmosphere. The space age brought new tools and new possibilities. The Pioneer 11 spacecraft flew past Saturn in 1979, but it was the Voyager missions that first gave us detailed looks at the Saturn system. Voyager 1 made its closest approach to Titan in November 1980, passing within 6,500 kilometers of the moon's surface. The images it sent back were simultaneously exciting and frustrating. Voyager's cameras revealed an orange globe, completely featureless, with no surface details visible at all. The atmosphere was so thick and hazy that visible light couldn't penetrate to the surface. But Voyager's instruments revealed something crucial. Titan's atmosphere was primarily nitrogen, about 95%, with methane making up most of the remainder. This was stunning because nitrogen is relatively rare in the outer solar system. How did Titan accumulate so much nitrogen? Where did it come from? These questions would drive planetary scientists for decades. Voyager 1 also discovered that Titan's atmosphere was far thicker than anyone had expected, extending hundreds of kilometers above the surface and creating multiple haze layers that gave the Moon its distinctive orange appearance. The spacecraft's instruments detected complex organic molecules in the upper atmosphere, evidence of ongoing chemistry that was creating the building blocks of life. But the surface remained hidden, a tantalizing mystery that would require new technology to solve. The frustration of seeing Titan's atmosphere but not its surface led mission planners to ensure that any future mission to Saturn would be equipped with radar capable of seeing through the haze. That future mission arrived at Saturn on July 1, 2004, when the Cassini spacecraft fired its main engine for 96 minutes to slow down and enter orbit around the ring giant. Cassini was a marvel of international cooperation, built by NASA, the European Space Agency, and the Italian Space Agency. It carried 13 instruments designed to study Saturn, its rings, and its moons in unprecedented detail. But perhaps the most anticipated aspect of the entire mission was the Huygens probe, a heat-shielded capsule designed by the European Space Agency to descend through Titan's atmosphere and land on the surface, becoming humanity's first ambassador to this distant world. On Christmas Day, 2004, Cassini released the Huygens probe toward Titan. For 20 days, Huygens coasted through space while Cassini maneuvered into position to receive the probe's transmissions. On January 14, 2005, Huygens slammed into Titan's upper atmosphere at over 18,000 kilometers per hour. The heat shield protected the probe from temperatures exceeding 1500 degrees Celsius as atmospheric friction slowed the spacecraft. At an altitude of about 150 kilometers, the main parachute deployed, and Huygens began its leisurely descent through Titan's atmosphere, a journey that would take 2.5 hours. During that descent, the probe's instruments sampled the atmosphere, measured temperature and pressure, detected winds and turbulence, and as it dropped below 20 kilometers altitude, the cameras finally had enough light to begin taking pictures. What those pictures revealed was astonishing. The surface of Titan looked remarkably Earth-like, with features that appeared to be drainage channels, river valleys, and what looked like a shoreline. The images showed rounded pebbles and cobbles, evidence of erosion and sediment transport. The probe landed in what appeared to be a dry riverbed or lakebed, with a relatively flat surface littered with smooth, rounded rocks, each about 10 to 15 centimeters across. The consistency of the surface was measured by an instrument designed to determine whether Huygens had landed on solid ground or in liquid. The surface had a thin crust with a softer material underneath, like walking on a sandy beach where your feet sink in slightly, or perhaps like fresh snow that has partially melted and refrozen. The temperature at the surface was measured at -179.5 degrees Celsius, and the atmospheric pressure was 1.46 times Earth's sea level pressure. But Huygens was just the beginning. For over 13 years, Cassini orbited Saturn, flying past Titan 127 times, each encounter revealing new details about this fascinating moon. The spacecraft's radar instrument could penetrate Titan's haze and create detailed maps of the surface. What Cassini discovered over those years revolutionized our understanding not just of Titan, but of planetary science itself. The radar revealed vast seas in Titan's polar regions, bodies of liquid methane and ethane hundreds of kilometers across and up to 200 meters deep. These weren't small puddles. These were genuine seas, the only stable bodies of surface liquid found anywhere in the solar system besides Earth. The largest, Kraken Mare, has a surface area larger than the Caspian Sea on Earth, stretching nearly 1,000 kilometers from end to end. The discovery of these liquid methane seas answered one of the biggest mysteries about Titan. Scientists had known for decades that methane in Titan's atmosphere was being destroyed by solar radiation, broken apart into hydrogen, which escapes to space, and carbon, which forms more complex organic molecules that rain out onto the surface. This process should have depleted all of Titan's atmospheric methane within about 50 million years, a tiny fraction of the age of the solar system. Yet Titan clearly had abundant methane in its atmosphere. There had to be a source replenishing the methane, and the seas provided at least part of the answer. But the seas alone weren't enough to solve the puzzle completely. The total amount of liquid methane and ethane on Titan's surface was less than what models predicted, suggesting that there might be vast subsurface reservoirs of liquid methane, possibly even a methane water table beneath the surface, analogous to groundwater on Earth. The more Cassini observed Titan, the more Earth-like the Moon appeared, despite the completely alien chemistry. Titan has clouds that form and dissipate, sometimes producing rain. The methane rain falls from the sky, just as water does on Earth, flowing into rivers and streams that carve valleys and canyons into the landscape. Some of these river systems extend for hundreds of kilometers, fed by seasonal rainfall that varies with Titan's year, which is equal to Saturn's orbital period of 29.5 Earth years. During Titan's winter in each hemisphere, clouds form over the polar regions and methane rain fills the lakes and seas. During summer, the liquids evaporate, creating dry lake beds in the lower latitudes. This methane cycle is remarkably similar to Earth's water cycle, with evaporation, cloud formation, precipitation, surface flow, and infiltration into the ground. Cassini's radar also revealed vast fields of sand dunes near Titan's equator, stretching across regions larger than deserts on Earth. These dunes are enormous, up to about 100 meters tall and hundreds of kilometers long, running in parallel lines across the landscape. But these aren't sand dunes made of silicon dioxide like Earth's deserts. Titan's dunes are made of organic particles, complex hydrocarbons that have precipitated from the atmosphere and been sculpted by winds into these massive structures. The presence of dunes tells us that Titan has wind, another similarity to Earth. The winds on Titan are generally light by Earth standards, typically just a meter or two per second at the surface, but the combination of dense atmosphere and low gravity means that even these gentle breezes can move particles and shape the landscape. Mountains rise from Titan's surface, some reaching over 3,000 meters in height. These aren't mountains of rock in the traditional sense. Remember, at Titan's surface temperature, water ice is as hard as granite, and that's what these mountains are made of, water ice mountains, carved by methane rivers, under orange skies. The geology of Titan is familiar yet alien, following the same physical principles that shape Earth, but with completely different materials playing the roles. Ice is rock, methane is water, and the whole system operates at temperatures that would instantly freeze any Earth organism solid. One of the most intriguing discoveries Cassini made was the detection of cryovolcanoes on Titan, or at least features that appear to be cryovolcanoes. These are volcanic mountains that erupt not with molten rock, but with water and ammonia mixtures, or possibly methane from underground reservoirs. The evidence isn't conclusive, and the scientific community continues to debate the exact nature of these features, but if they are indeed cryovolcanoes, they could be actively releasing methane into the atmosphere, helping to replenish the methane that's constantly being destroyed. This would solve the methane mystery and explain how Titan has maintained its methane atmosphere over billions of years. The potential cryovolcanic regions identified by Cassini show features that look like calderas and lava flows. But instead of molten rock, these flows would be slushes of water ice and ammonia, or possibly liquid methane erupting from underground chambers. But beneath all of this surface activity, Titan holds an even more profound secret. Deep beneath the icy crust, perhaps 50 to 100 kilometers down, Cassini's gravity measurements suggest that there's an ocean, a genuine water ocean, kept liquid by the heat of radioactive decay in Titan's core and possibly by tidal heating from Saturn's gravity flexing the moon as it orbits. This subsurface ocean is likely a mixture of water and ammonia, which acts as antifreeze, keeping the water liquid at temperatures well below 0 degrees Celsius. The evidence for this ocean comes from several sources: the way Titan responds to Saturn's tidal forces, the detection of extremely low-frequency radio waves that could be generated by an electrically conducting layer beneath the surface, and the overall density and moment of inertia of the moon, which suggests differentiation into layers with a liquid layer beneath the crust. The existence of this subsurface ocean is profound because it means Titan has two completely different environments where life might potentially exist. On the surface, you have a methane-based chemistry, operating at incredibly cold temperatures, where life, if it exists, would have to be utterly unlike anything on Earth, perhaps using methane as a solvent instead of water and breathing hydrogen instead of oxygen. This is purely hypothetical, and we have no evidence that life exists on Titan's surface, but the complex organic chemistry and the presence of liquid methane creates at least the theoretical possibility. In the subsurface ocean, conditions might be more familiar, with liquid water, dissolved minerals, and possibly organic material transported down from the surface or created through chemical reactions between the ocean and the rock beneath it. This environment, if it exists, could potentially harbor microbial life similar to extremophiles on Earth, organisms that live in deep ocean hydrothermal vents or in subglacial lakes in Antarctica. The organic chemistry happening on Titan is incredibly complex and is one of the main reasons scientists are so interested in this moon. The atmosphere is a giant chemistry laboratory, constantly producing complex organic molecules through photochemistry driven by ultraviolet light from the sun and through charged particle reactions driven by Saturn's magnetosphere. These processes create molecules called tholins, complex organic compounds that give Titan its characteristic orange color. Tholins aren't a specific molecule but rather a general term for the reddish-brown organic compounds that form when simple molecules like methane and nitrogen are exposed to ultraviolet radiation or electrical discharge. Similar tholins have been created in laboratory experiments here on Earth, designed to simulate conditions on Titan. What makes these tholins particularly interesting is that they contain many of the building blocks necessary for life as we know it. Laboratory analysis of synthetic tholins created under Titan-like conditions has revealed the presence of amino acids, the building blocks of proteins, and nucleotide bases, the building blocks of DNA and RNA. Now, this doesn't mean that life exists on Titan. The presence of amino acids and nucleotide bases isn't the same as having life, just as having bricks and timber doesn't mean you have a house. But it does mean that Titan is creating organic complexity on a massive scale. Over billions of years, these complex organic molecules have been raining down onto Titan's surface, accumulating in layers that could be substantial deposits of organic material, possibly mixed with ice and liquid methane. Some scientists have speculated about what kind of life could potentially exist in Titan's methane lakes. This would be life utterly unlike anything on Earth, based on completely different biochemistry. On Earth, all life uses water as a solvent, the medium in which biochemical reactions occur. Water has unique properties that make it excellent for this role. It's a polar molecule that can dissolve many different substances. It remains liquid over a relatively wide temperature range at Earth's surface pressure, and it has a high heat capacity that helps regulate temperature. Methane, on the other hand, is a nonpolar molecule with very different properties. It's liquid at much colder temperatures, it dissolves different kinds of molecules than water does, and any life that used methane as a solvent would have to have a completely different biochemical architecture. In 2015, a team of scientists published a theoretical study suggesting what kind of cell membrane could exist in liquid methane. They proposed a structure called an azotosome, made from nitrogen, carbon, and hydrogen, that could form a stable membrane in liquid methane, analogous to the lipid membranes that Earth life uses in water. This was purely theoretical chemistry, mathematical models showing that such structures could potentially be stable, but it demonstrated that at least on paper, you could imagine a form of life adapted to methane instead of water. Whether such life actually exists on Titan is entirely unknown, and most scientists consider it unlikely, but the possibility can't be completely ruled out. The Cassini mission ended on September 15, 2017, in a planned destruction dive into Saturn's atmosphere. After 13 years in orbit, the spacecraft was running low on fuel, and mission controllers wanted to ensure that Cassini wouldn't accidentally crash into and potentially contaminate Titan or Enceladus, another moon of Saturn that also shows potential for harboring life. In its final moments, Cassini transmitted data about Saturn's atmosphere composition right up until it lost contact with Earth, its last act of scientific discovery. The mission revolutionized our understanding of the Saturn system, and particularly of Titan, transforming it from a mysterious orange globe into a complex, dynamic world with its own weather, seasons, geology, and chemistry. But the story of Titan exploration is far from over. The scientific community recognized that Cassini had only scratched the surface, quite literally, of what Titan has to teach us. In 2019, NASA selected Dragonfly as the next mission to Titan, scheduled to launch in 2027 and arrive at Titan in 2034. Dragonfly isn't just another orbiter or lander. It's a rotorcraft, essentially a large drone that will fly through Titan's atmosphere, exploring multiple locations across the Moon's surface. The choice of a flying vehicle makes perfect sense for Titan. The thick atmosphere and low gravity make flight relatively easy. The rotors needed to keep Dragonfly aloft would be smaller and require less power than a helicopter on Earth, even though Dragonfly is much larger than any drone used on Earth. Dragonfly will land first near the equator in a region called Shangri-La, one of the vast sand dune fields that Cassini discovered. From there, it will make a series of flights, each one covering several kilometers, gradually working its way toward a region called Selk Crater, an impact crater about 90 kilometers in diameter where Cassini data suggests that liquid water once existed on the surface, at least temporarily. When a large meteorite impacts Titan, the energy of the impact melts water ice, creating liquid water that can persist for hundreds or even thousands of years before refreezing. During that time, the liquid water would be in contact with all the organic material on Titan's surface, creating conditions where complex chemistry could occur. It's even possible, though speculative, that some form of prebiotic chemistry or even simple life could have originated in these temporary liquid water environments, though whether such life could persist after the water refroze is highly doubtful. Dragonfly's instruments will analyze the composition of Titan's surface materials, looking for complex organic molecules and trying to understand the chemistry that produces them. The spacecraft will also study Titan's atmosphere, measuring how it varies from place to place and over time. It will search for evidence of biological signatures, though finding such evidence is considered a long shot. Perhaps most importantly, Dragonfly will help us understand whether Titan's organic chemistry represents a frozen stage of the chemistry that led to life on Earth. By studying Titan, we might be able to understand the chemical steps that occurred on Earth before life emerged, steps that are now hidden on our own planet because life has so thoroughly transformed Earth's atmosphere and surface. The question of life on Titan remains open, and it's important to be clear about what we mean by this question. There are really two separate questions. First, could life exist in Titan's surface environment, in the methane lakes and rivers, using biochemistry utterly unlike anything on Earth? The honest answer is that we don't know, but most scientists would say it's unlikely simply because we don't have any evidence for it and because such life would require solving numerous difficult biochemical problems. The chemistry would have to work at incredibly cold temperatures where molecular motion is very slow, which would make metabolism and reproduction extremely difficult. But unlikely isn't the same as impossible, and until we've thoroughly explored Titan, we can't rule it out. The second question is whether life could exist in Titan's subsurface ocean. This seems more plausible to many scientists because the environment would be more similar to environments on Earth where we know life exists. Liquid water, dissolved minerals, organic material from the surface filtering down through cracks in the ice, possibly hydrothermal activity at the ocean floor where Titan's rocky core meets the water. These are conditions that at least resemble places on Earth where life thrives. But again, we simply don't know. We haven't directly detected this ocean, much less sent a probe to explore it. The evidence for its existence is strong but indirect, based on gravity measurements, magnetic field data, and models of Titan's interior structure. If we want to search for life in Titan's subsurface ocean, we would need a mission far more ambitious than anything currently planned. We would need a lander that could drill or melt through 50 to 100 kilometers of ice, or find a place where the ocean is accessible through cracks or cryovolcanic vents, and then deploy a submersible to explore the ocean. This is technology that doesn't currently exist, though concepts for such missions have been proposed. Some scientists have suggested that we might be able to sample Titan's subsurface ocean without drilling through the ice by analyzing the composition of cryovolcanic eruptions, if such eruptions are indeed occurring. If water and other materials from the subsurface ocean are being ejected onto the surface through cryovolcanism, we could study those materials to learn about ocean composition and search for biosignatures. The comparison between Titan and Earth is both illuminating and humbling. These two worlds, separated by over 1 billion kilometers, are more similar to each other than any other two bodies in the solar system, yet they're also profoundly different. Both have thick nitrogen atmospheres. Both have weather systems with clouds, precipitation, and seasonal variations. Both have liquids on their surfaces that cycle between atmosphere, surface, and subsurface. Both have complex geology with mountains, valleys, plains, and possibly active geology reshaping the surface. Both have organic chemistry occurring on a massive scale. Yet one is a warm world where water is liquid and life flourishes everywhere, while the other is a frozen world where methane plays water's role in life, if it exists at all, remains hidden and hypothetical. Understanding why these two worlds evolved so differently is one of the fundamental questions in planetary science. Both Earth and Titan likely formed from the same basic materials, the dust and gas of the solar nebula, though Earth formed closer to the Sun where it was warmer and Titan formed in the cold outer solar system. The temperature difference explains why Earth's volatiles are primarily water while Titan's are methane and nitrogen. But there are deeper questions. How did Earth develop plate tectonics and a magnetic field while Titan apparently did not? Why did Earth develop life that transformed its atmosphere while Titan, with all its organic chemistry, remains apparently lifeless. How did Earth maintain liquid water on its surface for billions of years while Titan's surface water remains frozen solid? These questions aren't just about understanding two individual worlds. They're about understanding the range of possible planetary environments and what factors determine whether a planet or moon becomes habitable. As we discover more exoplanets orbiting other stars, we're finding that planetary systems are incredibly diverse. Some planets orbit so close to their stars that their surfaces are molten. Others are so far away that all their atmospheres have frozen onto the surface. Some giant planets orbit closer to their stars than Mercury orbits our Sun. This diversity suggests that there might be many worlds in the galaxy with conditions unlike anything in our solar system. But there might also be worlds similar to Titan, cold moons orbiting giant planets, with thick atmospheres and organic chemistry, and by understanding Titan, we might be able to understand those distant worlds as well. Titan also challenges our assumptions about habitability. For decades, the search for life in the universe has focused on finding planets in the habitable zone, the region around a star where temperatures are right for liquid water to exist on a planet's surface. Earth is in the Sun's habitable zone, and liquid water is essential for life as we know it, so this focus makes sense. But Titan reminds us that habitability might be more complex than just having the right temperature. Titan is far outside the Sun's habitable zone, yet it has liquid on its surface and possibly a subsurface ocean. Europa, Enceladus, and several other moons in the outer solar system also have subsurface oceans despite being far from the Sun. These moons are kept warm by tidal heating, the gravitational interaction with their parent planets flexing and heating their interiors. This means that moons orbiting giant planets might be habitable even if the giant planet itself is far from its star's habitable zone. If this is true, the number of potentially habitable worlds in the galaxy could be much larger than we thought. For every star with a planet in its habitable zone, there might be multiple giant planets with multiple moons, some of which could have subsurface oceans. Some scientists estimate that there could be more habitable moons than habitable planets in the galaxy. This would profoundly change our understanding of where to search for life and would suggest that life might be more common in the universe than we previously imagined. Titan, with its complex organic chemistry and possible subsurface ocean, might represent a whole class of worlds that we're only beginning to understand. The organic material on Titan's surface is another resource that future human explorers might find valuable, though we're talking about a future so distant it's barely worth speculating about. If humanity ever develops the technology to travel routinely to the outer solar system, Titan's abundant organic material could be useful for manufacturing plastics, fuels, and other carbon-based materials. The thick atmosphere would provide radiation shielding, protecting human explorers from cosmic rays and solar radiation. The low gravity would make it relatively easy to launch spacecraft from the surface. Some futurists have even suggested that Titan could become a hub for human activity in the outer solar system, though this is highly speculative and would require technological advances we can barely imagine today. More immediately, Titan serves as a natural laboratory for studying prebiotic chemistry, the chemistry that occurred before life emerged. On Earth, the evidence of this prebiotic chemistry has been largely erased by 4 billion years of biological activity and geological processes. Life transformed Earth's atmosphere, oceans, and rocks, overriding the chemical signatures of the prebiotic world. But Titan might preserve that early chemistry, frozen in time at cold temperatures that slow chemical reactions to a crawl. By studying what's happening on Titan today, we might understand what happened on Earth 4 billion years ago, before the first living cells emerged. This could help us understand one of the most profound questions in science: how does life begin? What are the chemical steps that lead from simple organic molecules to self-replicating systems that we would recognize as alive? Scientists have attempted to recreate Titan's atmospheric chemistry in laboratories here on Earth, subjecting mixtures of nitrogen and methane to ultraviolet light or electrical discharges to simulate lightning. These experiments produce a brownish gunk that's remarkably similar to the tholins on Titan. When analyzed, this lab-created material contains dozens or even hundreds of different organic compounds, including some of the same amino acids found in living organisms. This demonstrates that complex organic chemistry can arise spontaneously from simple starting materials given the right conditions and energy sources. But going from this complex organic chemistry to actual life is an enormous step that we still don't understand. The gap between complex organic molecules and even the simplest living cell is vast, and bridging that gap requires solving numerous difficult problems. How do you get reliable replication? How do you develop metabolism to harvest energy? How do you create a barrier between inside and outside, the cell membrane that defines the boundary of life? These are questions that studying Titan might help us answer, or at least might help us frame more precisely. The seasonal variations on Titan are also fascinating and reveal a world that's constantly changing. As Saturn orbits the Sun, different parts of Titan receive different amounts of sunlight, creating seasons that last about 7.5 Earth years each. During northern winter, the North Pole is tilted away from the Sun and experiences months of continuous darkness, while the South Pole has continuous daylight. This creates a polar vortex in the northern hemisphere, a massive swirling system of clouds and winds that concentrates trace gases and hazes over the North Pole. As the seasons change and the North Pole tilts toward the Sun, this polar vortex dissipates and reforms over the South Pole. The liquid methane seas in the polar regions also respond to these seasonal changes, with evaporation and precipitation varying as the amount of sunlight changes. Cassini arrived at Saturn during southern summer on Titan, and over 13 years in orbit, the spacecraft watched as autumn came to the southern hemisphere and spring arrived in the north. The changes were dramatic. Clouds that had been common in the southern hemisphere became rare, while clouds began forming over the northern lakes and seas. The polar vortex that had dominated the northern atmosphere dissipated and began forming in the south. These observations showed that Titan's climate system is dynamic and responsive, driven by the same basic physics that drives Earth's climate, the unequal heating of different latitudes by the Sun, even though the specific details are very different. One of the surprising discoveries about Titan's atmosphere was the presence of heavy organic molecules much higher in the atmosphere than models had predicted. Cassini detected molecules containing dozens of atoms at altitudes of over 1,000 kilometers, far above the main haze layers. These molecules shouldn't be able to reach such high altitudes based on their weight and the expected atmospheric mixing. Some scientists have proposed that these molecules might form at high altitudes rather than forming lower down and being lofted upward. Others have suggested that electrostatic forces might be involved, with charged particles carrying the organic molecules upward. Understanding how these large organic molecules reach the upper atmosphere is important for understanding Titan's atmospheric chemistry and evolution. The interaction between Titan and Saturn's magnetosphere also shapes the Moon's atmosphere and surface. Saturn has a powerful magnetic field that traps charged particles, creating radiation belts similar to Earth's Van Allen belts. As Titan orbits through this magnetosphere, charged particles strike the Moon's upper atmosphere, driving chemical reactions and contributing to the formation of complex organic molecules. During part of its orbit, Titan actually moves outside Saturn's magnetosphere and is directly exposed to the solar wind, the stream of charged particles flowing out from the Sun. This creates additional complexity in Titan's atmospheric chemistry, with different processes dominating depending on whether the Moon is inside or outside the magnetosphere. The surface of Titan, as revealed by Cassini's radar and by the Huygens probe, is younger than scientists expected. Impact craters are relatively rare, suggesting that geological processes are resurfacing the Moon and erasing craters over time. On Earth, plate tectonics, erosion, and volcanic activity constantly reshape the surface, burying or destroying old impact craters. Titan doesn't have plate tectonics, but it does have erosion from methane rainfall and possibly cryovolcanism. The lack of many visible impact craters suggests that these resurfacing processes are active and efficient, maintaining a relatively young surface despite Titan being over 4 billion years old. Some regions of Titan's surface might be only a few 100 million years old, very young in geological terms. The exact composition of Titan's lakes and seas was difficult to determine from Cassini's data. The radar observations showed that the liquids were smooth and reflective, consistent with liquid hydrocarbons, but determining the exact mixture of methane and ethane required careful analysis of how the radar signals reflected from the surface. Different studies produced different results, but the general consensus is that the lakes and seas are primarily liquid methane with dissolved ethane and other hydrocarbons, possibly with some nitrogen dissolved as well. The exact composition probably varies from lake to lake and with depth. The large seas like Kraken Mare might be deep enough to have stratification, with different compositions at different depths, similar to how Earth's oceans have different salinity and temperature at different depths. One intriguing possibility is that Titan's seas might have waves. On Earth, wind blowing across the surface of water creates waves, and the same physics should apply on Titan. However, Cassini's radar observations showed the surfaces of Titan's lakes and seas to be incredibly smooth, like mirrors, with no evidence of waves. This was puzzling because Titan definitely has winds, and those winds should create waves on the liquid surfaces. Several explanations have been proposed. Perhaps the winds at the surface are too light to generate waves, or perhaps the surfaces are calm because Cassini always observed during seasons when the polar regions were relatively quiet meteorologically, or perhaps there's something about the physics of liquid methane that suppresses wave formation. Some scientists have proposed that waves do exist but are small and that Cassini's radar simply wasn't sensitive enough to detect them. Future missions like Dragonfly might be able to settle this question by making direct observations of the lakes and seas. The composition of Titan's surface is complex and varies from place to place. The bright regions visible in radar images are thought to be areas where relatively pure water ice is exposed at the surface, while dark regions are areas covered with organic material, the tholins and other hydrocarbons that have rained out of the atmosphere. The dune fields at the equator are made of organic particles, likely small grains of solid hydrocarbons that have been blown into these massive formations by winds. The mountains and highlands are probably water ice bedrock, possibly mixed with other ices like carbon dioxide or methane frozen solid. The lowlands and lake beds might have thick deposits of sediment, organic material mixed with ice particles, accumulated over millions of years. Understanding how all these different materials are distributed across Titan's surface and how they interact with each other is crucial for understanding the Moon's geology and chemistry. The organic material on the surface isn't just sitting there inert. It's constantly being cycled through the environment. Methane rain falls on the surface, dissolves some of the organic material, carries it into rivers and lakes, where it might be deposited as sediment or might evaporate back into the atmosphere. Some organic material might be buried and transformed by heat and pressure in Titan's interior, possibly creating even more complex molecules. Some might be broken down by radiation or by chemical reactions with water ice. This active cycling of organic material makes Titan's surface a dynamic environment despite the incredibly cold temperatures. The nitrogen in Titan's atmosphere presents another mystery. Nitrogen is relatively rare in the outer solar system, so where did Titan get so much of it? The leading theory is that the nitrogen was originally in the form of ammonia ice mixed with water ice when Titan formed. Ammonia is much more common in the outer solar system than nitrogen gas. Over time, ultraviolet radiation and impacts broke apart the ammonia molecules, releasing nitrogen gas into the atmosphere and hydrogen that escaped to space. This process would have occurred early in Titan's history and would explain why the atmosphere is now dominated by nitrogen. But this theory has some problems. The isotopic composition of nitrogen in Titan's atmosphere doesn't quite match what we would expect from this process, suggesting that the story might be more complicated. Some scientists have proposed that Titan accreted both ammonia ice and nitrogen-rich organics, or that some nitrogen was delivered by later impacts of comets. The methane mystery I've mentioned before remains one of the biggest unsolved questions about Titan. We know that methane is being destroyed in the atmosphere on timescales of tens of millions of years. We know that there are liquid methane seas on the surface that serve as a reservoir. But the total amount of methane in the seas and atmosphere isn't enough to have lasted through billions of years of destruction unless there's a source replenishing it. The leading candidates for this source are cryovolcanism bringing methane up from the interior, and vast subsurface reservoirs of methane that seep up to the surface over time. Some scientists have even proposed that methane is being created by chemical reactions in the subsurface ocean, though this seems less likely than methane trapped during Titan's formation being slowly released. If we don't figure out where Titan's methane is coming from, we might be looking at a Titan that has changed dramatically over its history. Perhaps billions of years ago, Titan had far more methane in its atmosphere and on its surface. Perhaps the lakes and seas were once much more extensive, covering large portions of the moon. As the methane was destroyed and not fully replenished, the seas shrank to their current size, confined to the polar regions where temperatures are coldest and evaporation is slowest. In the future, if the methane continues to be depleted, Titan might eventually lose its lakes and seas entirely, becoming a world with only a thin methane haze in its atmosphere, with most of the surface covered in organic material deposited from that haze. This would be a Titan very different from what we see today, a frozen desert world covered in organic snow. Alternatively, if there are indeed vast subsurface reservoirs of methane, or if cryovolcanism is actively releasing methane from the interior, then Titan might maintain its current state for billions of years into the future. The moon might even have cycles where methane abundance increases and decreases over geological timescales, driven by variations in cryovolcanic activity or by changes in how efficiently methane can seep up from subsurface reservoirs. Understanding which of these scenarios is correct will require future missions that can directly measure or infer the amount of methane beneath Titan's surface, a challenging task given that we would need to probe beneath kilometers of ice and organic material. The future exploration of Titan promises revelations that could fundamentally alter our understanding of our place in the cosmos. When Dragonfly launches in the late 2020s and arrives in the mid-2030s, it will carry instruments capable of analyzing Titan's organic chemistry with a precision that Cassini could never achieve. The rotorcraft will sample materials from multiple locations, comparing the organic composition of sand dunes with that of ancient lakebeds, examining impact craters where liquid water might have temporarily existed, and potentially even sampling the shores of methane seas. Each location will tell a different part of Titan's story, revealing how organic molecules are created, transported, and transformed across this alien landscape. But Dragonfly is just the next step. Scientists are already dreaming of missions beyond it. Concepts have been proposed for floating probes that would drift on Titan's methane seas, submarine vessels that could dive beneath the surface of Kraken Mare, balloons that would float through the atmosphere for months or years, and even submarines designed to melt through the ice shell and explore the subsurface ocean. Each of these missions would answer different questions about Titan and might raise entirely new ones. The floating probes could measure wave action, study how organic material is deposited in the seas, and search for any chemistry occurring in the liquid methane. A balloon could measure how Titan's atmosphere varies with altitude and location, tracking seasonal changes and searching for active cryovolcanism by detecting plumes of water vapor. A subsurface ocean explorer could search for hydrothermal vents, measure water chemistry, and directly search for signs of life in Titan's hidden ocean. These missions remain concepts, unfunded dreams that might or might not become reality depending on budget priorities, technological developments, and scientific discoveries. But the fact that such missions are being seriously discussed shows how profoundly Titan has captured the imagination of the planetary science community. This moon, once just an orange blur in our telescopes, has become one of the most compelling targets for exploration in the entire solar system, a world that challenges our assumptions about habitability, offers insights into Earth's ancient past, and might harbor environments where life could exist in forms we've never imagined. The story of Titan is ultimately a story about the diversity and complexity of worlds in our solar system and beyond. For centuries, humans imagined that other worlds would be similar to Earth, perhaps with different geography but fundamentally recognizable. We imagined Martians living on a Mars that was essentially Earth-like, Venusians dwelling in the jungles of Venus, civilizations on every planet and moon. As we've actually explored the solar system, we've discovered that each world is unique, shaped by its own particular combination of composition, distance from the Sun, size, and history. Mars is a frozen desert with ancient river valleys carved when the planet was warmer and wetter billions of years ago. Venus is a hellish greenhouse with surface temperatures hot enough to melt lead and atmospheric pressure that would crush a submarine. The moons of Jupiter and Saturn are worlds of ice and rock, some with subsurface oceans, others with active geology that resurfaces them in geologically short time frames. Titan stands out even among this diversity as a world that is simultaneously familiar and utterly strange. The presence of stable surface liquids, weather systems, seasonal variations, and complex organic chemistry make it the most Earth-like world in the solar system apart from Earth itself. Yet the chemistry is completely different, operating at temperatures that would freeze any Earth organism solid in seconds, using methane where Earth uses water, creating landscapes of water ice mountains and rivers of liquid natural gas. This combination of familiar processes operating with unfamiliar materials makes Titan an invaluable laboratory for testing our understanding of how planets and moons work, how chemistry creates complexity, and how environments might support life. As we look to the future, to the possibility of finding life elsewhere in the universe, Titan reminds us to keep our minds open about what forms that life might take and where it might exist. The universe is vast beyond human comprehension, with hundreds of billions of galaxies each containing hundreds of billions of stars, many or most of which likely have planets and moons. Among those countless worlds, there will be diversity we can barely imagine, environments nothing like Earth or Titan or anything in our solar system. Some might harbor life based on chemistry we haven't even thought of yet, thriving in conditions we would consider impossible. By studying Titan, by pushing our understanding of what chemistry can do and where habitability might exist, we prepare ourselves for the discoveries that await us as we continue exploring the cosmos. Titan also serves as a humbling reminder of how much we still don't know and how much there is yet to discover even in our own cosmic neighborhood. Despite over a decade of intensive study by one of the most sophisticated spacecraft ever built, fundamental questions about Titan remain unanswered. We don't know definitively whether a subsurface ocean exists, though the evidence strongly suggests it does. We don't know the source of the methane that replenishes the atmosphere. We don't know whether cryovolcanism is currently active or extinct. We don't know the full inventory of organic molecules on the surface or whether any prebiotic chemistry is occurring. We certainly don't know whether life exists anywhere on or in Titan. Each answer we find seems to raise new questions, revealing deeper layers of complexity and driving us to explore further. This endless frontier of discovery is what makes planetary science so compelling and so important. Every world we study teaches us something not just about that particular world, but about how planetary systems form and evolve, about the chemistry that creates complexity, about the conditions necessary for life. The knowledge we gain exploring Titan will help us understand Earth's history, will inform our search for life on other worlds, and will expand human knowledge in ways we can't fully predict. Some of the most important discoveries in science have come from unexpected places, from pursuing questions out of pure curiosity without knowing where they would lead. Titan exemplifies this kind of exploration, a world we study because it fascinates us, because it challenges us, because we want to understand it, and in doing so we advance human knowledge in profound and sometimes unexpected ways. Standing on Titan's surface today, if you could survive the cold and the alien atmosphere, you would see a landscape both beautiful and strange. The orange sky above, perpetually hazy, filtering the sunlight into a dim twilight glow. The terrain around you, perhaps a field of organic sand dunes stretching to the horizon, or the shore of a methane sea lapping gently against the beach, or the craggy peaks of water ice mountains rising into the haze. In the distance, weather systems might be visible, clouds forming and dissipating, perhaps a methane rainstorm darkening the sky. Beneath your feet, organic material accumulated over billions of years, the chemical legacy of eons of atmospheric reactions. And far above, invisible through the thick atmosphere, Saturn would be hanging in the sky, a giant presence dominating the heavens of this distant moon. This is Titan. A world of methane seas and organic chemistry, of atmosphere and weather and seasons, of mysteries both solved and unsolved. A world that shows us how planets can be both similar to and different from Earth, operating by the same physical laws but with utterly different materials and conditions. A world that might harbor life in forms we've never imagined, or might be completely lifeless yet still profoundly important for understanding how life begins. A world that represents both the culmination of decades of exploration and the beginning of a new chapter in our understanding of the solar system. As we continue to explore Titan, as Dragonfly flies through its skies and future missions probe its secrets even more deeply, we move closer to answering some of the most fundamental questions humans have ever asked. Are we alone? How did life begin? What other wonders await us in the cosmos? Titan won't answer all these questions, but it will help us understand them better, and in doing so, it will expand the boundaries of human knowledge and remind us of the incredible universe we inhabit. This frozen moon at the edge of the solar system, shrouded in orange haze, might hold keys to understanding our own origins and our place among the stars. Claude is AI and can make mistakes. Please double-check responses.